Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International A-Level Chemistry Unit 2 for May 2023. Let's begin with the first question. Question 1 says the enthalpy level diagram for a reaction is shown. So this is the enthalpy level diagram. We have the enthalpy on the vertical axis and progress of reaction, and then the reactants and the products. This is an exothermic reaction. They say which is represented by this diagram. If you look at A, this is converting a solid into a gas. This is going to be endothermic. Energy has to be supplied, so A is wrong. This is also breaking away. This is ionization. It's endothermic. And then this is dissolution of ammonium nitrate. That is going to be endothermic. The only exothermic one is this because this is bond formation. A bond is formed. Heat is going to be released, so the answer should be a C. In question 2, excess zinc powder is added to 50 grams of 0.5 mol per decimeter cubed copper 2 sulfate solution in a polystyrene cup. The mixture is stirred and the maximum temperature change determined. The enthalpy change for the reaction is calculated to be negative 185 kilojoules per mole. The data book value for this reaction is negative 217 kilojoules per mole. So for this experiment, we're going to compare the data booklet value as well as the calculated value. The error is going to be the difference between the two. And since the data booklet value is going to be the true value, we're going to get the error by getting this minus that. So that minus that, the error is going to be negative 32. And that means the percentage error should be negative 32 divided by the true value times 100, giving us 14.7%, and the answer is going to be a C. In part B, in the calculation, the specific capacity of the liquid is taken to be 4.18 joules per gram per degree Celsius, rather than the true value, which is 3.85 joules per gram per degree Celsius. They say the use of 4.18 joule per gram per degree Celsius in the calculation. If you look at the question, using a specific capacity this rather than that, it means we are going to get a higher delta H. And this delta H is going to be closer to the actual delta H value or the true value, or you could say the data booklet value. So this is going to lower the error, meaning the difference between this calculated value and the data booklet value is going to be less. So it's going to lower the error in the final value obtained. So the answer should be B. And in question 3, the enthalpy changes for two reactions are shown. So we have this reaction here and that reaction. They say what is the enthalpy change for the reaction between iron 3 oxide and carbon. So this is the reaction we're talking about. It means I have to look at these two reactions and reverse one of them in order to generate this final equation. So since iron oxide is on the left, I'm going to reverse this equation, reverse it so that this comes this way and those go the other side. This is what I get, then combine the two. Oxygen is going to cancel out because it's going to be on different sides of the combined equation. You can see this one here. We combine like that. That cancels with that. I remain with this, which is there. I remain with carbon, which is that. And then iron on this side as well as carbon monoxide the other side. Because I reversed this, I reversed the sign as well. So just add them together. I got 491 kilojoules per mole. And the answer is going to be A. In question 4, which of these alkanes would be expected to have the highest boiling temperature? So here we have to look at the number of carbons. We can see 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Those are isomers. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7. This one has more carbons in comparison to the others. Even if it has more branches, it has more number of electrons. And therefore will form more London forces, so the answer is going to be a D. In question 5, the boiling temperature of hexane is 69 degrees Celsius, and that of cyclohexane is 81 degrees Celsius. The main reason that cyclohexane has a higher boiling temperature is that cyclohexane molecules, the compounds we're comparing are both alkanes. The number of London forces formed are going to be greater in the one with a higher boiling point, which is cyclohexane, in comparison to just hexane. So the answer should be a C. In question 6, the structures and boiling temperatures of butane and propanol are shown. So here we have the boiling point, 0 degrees, and this is going to be 49. They say the main reason that propanol has a higher boiling temperature is that propanol molecules, if you look at the number of electrons, and again, I did this already, so we have, these are going to be 6, 7, 8, 9. There are 9 electrons here, 8 here, 8 here, and 9. Total is 34 electrons. And here we have 9, we have 8, here we have 6, and here we have 8, and 1. Total is going to be 32. So the only difference is because one has permanent dipoles. We can see the carbon and oxygen bond. This is partially positive, that's partially negative. It has permanent dipoles between the molecules, and that's why it's going to have a higher boiling point in comparison to this. In question 7, hydrogen bonds are formed when methanol dissolves in water. Which structure best represents a hydrogen bond between methanol and water? And again, this question is looking at which one best represents. This is the best representation because we can see there is the first molecule and then the water molecule, and the bond angle here is 180. If we look at this, the bond angle is not 180, so that is out. When we look at this, the hydrogens directly attached to carbon never take part in hydrogen bond formation, so this is out. And this one here, the water molecule, is interacting with a hydrogen that is attached to the carbon, so this is going to be wrong, so the only correct answer should be A. In which pair of compounds is the stated element in the same oxidation state? Again, I already calculated this, so this one here we have +7, +5, different. These are going to be the same, it's both +6, +6, +7, -2, -1, so the only answer here is going to be both chromiums are going to be +6 oxidation state. And next I say, what is the formula of barium-2 ferrite-6? If it's barium-2 ferrite-6, barium is +1, then this is going to be +4, so that's out. Here we have 2 plus and the other is going to be 4. Here we have 1 plus, the other is going to be 6. And here we have 2 plus, the other is going to be 6. So the answer is going to be a D. Question 10. When lithium reacts with excess oxygen, only lithium oxide is formed. When sodium reacts with excess oxygen, sodium oxide and sodium peroxide are formed, which is the main reason why sodium peroxide is formed. If you look at the two, remember here they've told us only lithium oxide is formed. I showed you something here. If sodium reacts with oxygen, we can form sodium oxide and sodium peroxide. So lithium will have greater positivity or a greater positive field around it. So it will attract the oxygen strongly, leading to just formation of lithium oxide, meaning one lithium and one oxygen bonded together strongly. Now when we go to sodium, which is bigger, sodium is going to attract the oxide less, and this is going to allow an oxide-oxide interaction we see here. Because this is bigger, the attraction to the oxygen is going to be smaller or weaker, and this is going to lead to an attraction between the oxide and the oxide, allowing the formation of a peroxide. So the suitable answer should be the sodium ion has a larger radius than the lithium ion. In question 11, a piece of sodium weighing 1.15 grams reacts completely with distilled water, and the solution formed is made up to 250 centimeters cubed. So this is the equation for the reaction. They say, what is the concentration of sodium hydroxide solution? For sodium, the number of moles are going to be the mass divided by the atomic mass, and I got 0.05, so those are the moles of sodium. So to find the moles of sodium hydroxide, I'm going to use the moles of sodium. The ratio is 2 to 2, which is basically 1 to 1. So the number of moles are going to be the same, which is 0.05 mole. And so the concentration is equal to number of moles divided by volume. Using my calculator, I got 0.2 mole per decimeter cubed, and the answer is going to be a D. In question 12, magnesium nitrate decomposes on heating. We can see the equation. They say a sample of magnesium nitrate decomposes completely. The total volume of gas formed was 1,200 centimeters cubed, measured at room temperature and pressure. What mass of magnesium nitrate was used? So they've given us the molecular mass of that as well as the molar gas volume. So I calculated this from here. I began by looking at the volume of oxygen, which is going to be 1/5, times the volume, the total volume of gas that was formed. In the end, we should have gases oxygen as well as nitrogen dioxide. So if this is the total, the volume of oxygen should be 1/5. Remember that total is 4 plus 1, giving us 5. So 1/5 times 1,200, and this is 240 centimeters cubed. So the number of moles of oxygen are going to be the volume of gas divided by volume molar using the molar gas equation. And I got 0.01 mole of oxygen. So working backwards, the mole ratio is 1 to 2. The moles of magnesium nitrate are going to be 2 times 0.01, which is 0.02 mole. And so the mass is going to be number of moles times mR, which is 0.02 times 148.3, giving us 2.97 grams as the answer. In question 13, when solid sodium chloride is placed in a Bunsen burner, a persistent yellow color is observed. The yellow color is due to, in a Bunsen flame, this is a flame test, the yellow color is due to electrons transitioning, and then as they come back to the ground state, energy is going to be released, which has a wavelength corresponding to that yellow color in the visible region. So the answer should be electrons being excited to high energy levels and emitting yellow light on returning to the ground state. So that should be the answer. In question 14, in a series of experiments, the time taken to complete the reaction between iron 3 sulfate and sodium thiosulfate in aqueous solution is measured. 1 drop of a solution of a substance is added to separate reaction mixtures. The results are shown. So here's the information in the table. We can see the reaction times and then the substances that were added. They say which ion speeds up this reaction. If there is no substance, the reaction time is 205. But here we can see when there is copper 2 sulfate, this has the least reaction time. Therefore, it's going to be copper. So the answer should be A. In question 15, hydrogen peroxide decomposes in the presence of a catalyst. This is the equation for the decomposition. They say the volume of gas formed is measured at regular time intervals and the data plotted on a graph. So that is the graph. Down here they say what is the rate of formation of oxygen at point X. If they want you to find the rate at point X, you need to draw a tangent to the curve at point X and then find the gradient of that tangent. So I drew my tangent like that and I got this point 0.5, 12.5 and 7.5, 22.5. I used those to calculate my gradient and my gradient was 1.4. Since 1.3 is closest to 1.4, I took my answer to be A. And again, the gradient is going to be varied. I'm using the PDF version and the actual paper could be more spread out. So there are tiny variations that could be in the answer. Maybe if you use the actual paper, you could have maybe an answer very close. In question 16, the structures of 3 bromoalkanes P, Q, and R are shown. They say which of these bromoalkanes may be classified as tertiary. Here the Br is on a carbon attached to 2 carbons, so this is secondary. Here the Br is on a carbon attached to only 1 carbon, so this is primary. And here the Br is attached to a carbon attached to 3 other carbons, so that's tertiary. So the answer should be R only. In question 17, when 1 chlorobutane is mixed with ethanol and aqueous silver nitrate, a reaction occurs. Which species is the nucleophile in this reaction? This is a reaction in which we get an alcohol in the end because this is ethanol and aqueous silver nitrate. The silver in silver nitrate takes away the Cl, and then the OH in the water or in the aqueous layer comes and substitutes. So this is going to be the nucleophile. It's going to be water. In question 18, propan-1-ol may be converted into propene. This is the reaction. They say which reagent is used in this reaction. Here we use concentrated phosphoric acid. So the answer should be that. And then the reaction is best classified as, this is going to be elimination because a hydrogen is lost from here and an OH from here to form water. So the answer should be A here. So this brings us to the end of section A. Let's continue to section B. In question 19, some reactions of halogenoalkanes are summarized in the diagram. So here we see this being converted to this. We should use ammonia. And then this converted to that. We could use potassium hydroxide in aqueous conditions. And this converted to that. We're going to produce a nitrile, so that should be potassium cyanide in ethanol. They say name the type and mechanism of these reactions. They're all nucleophilic substitution reactions because nucleophiles come in as they substitute other nucleophiles. Then they say give the IUPAC name of the structure M. This is going to be a nitrile because CN will come in this place. It's going to be this structure here. So this is going to be the main chain, carbon 1, carbon 2, carbon 3. So it's a propane nitrile. And there are 2 methyls on carbon 2. So we say 2,2-dimethyl propane nitrile. That is going to be the name. Then they say state the reagent and conditions required for reaction 1. Like I said already, we'll need ammonia, but ammonia is a gas. It has to be under pressure or in a sealed tube. So I said alcoholic ammonia, you heat under pressure or heat in a sealed tube. In part D, an incomplete mechanism for reaction 2 is shown. So they say complete the mechanism by adding alkali arrows and relevant dipoles and lone pairs. This is a tertiary halogenoalkane. It means the Br has to go away first to leave a carbocation. So I put a partial plus, partial minus. The Br breaks away, creating this. And then the hydroxide comes in, donating the lone pair of electrons to the carbocation, producing what we see here. The next they say describe how intermediate J is formed. In the first step, naming the process that occurs. Initially, this bond breaks heterolytically. Br takes both electrons. We can see that's why it becomes Br minus. So I said heterolytic fission occurs, breaking the carbon Br bond. The bond pair of electrons is transferred to bromine atom, forming bromide and the carbocation intermediate. And next they say state the shape of intermediate J and justify your answer. Intermediate J, which is this one here, is going to be planar. So it's trigonoplanar because it contains 3 bond pairs and no lone pairs. So the bond pairs rearrange themselves into a trigonoplanar shape to minimize repulsion. And next they say the product of reaction 2 is shown, which is this one here. This compound has 3 isomers that are also alcohols. Draw the structures of these isomers. So this is a tertiary alcohol, so I drew the primary alcohol. Then there is a secondary alcohol and another primary alcohol, so 2 primaries and 1 secondary. In part E, they say the reaction of halogenoalkanes with hydroxide ions is often carried out using sodium hydroxide and potassium hydroxide. An alternative is moist silver 1 oxide, which is prepared by adding a few drops of water to solid silver 1 oxide. Silver 1 oxide is insoluble in water but produces sufficient hydroxide ions for the reaction. Write the ionic equation for the reaction of silver 1 oxide with water. State symbols are now required. Silver 1 oxide plus water gives us silver plus hydroxide. And again, this is because they said it's insoluble in water and produces sufficient hydroxide ions for this reaction. So if hydroxide ions are to be produced, it means the OH here that leaves silver alone, which is going to be the silver ion. Together we'll have the silver hydroxide. Next they say suggest one advantage of using silver 1 oxide rather than sodium hydroxide or potassium hydroxide. So remember from this question they told us silver 1 oxide is insoluble, so we can just separate it out by filtration. Yet if we had used sodium hydroxide or potassium hydroxide, those are not soluble and it will be harder for them to be removed. So I said insoluble silver 1 oxide is easily removed or separated from the reaction mixture at the end of the reaction. This is because we can filter it out. So this brings us to the end of question 19. Let's continue to question 20. In question 20, this question is about fuels. The enthalpy change of combustion is the maximum amount of heat energy that can be obtained by the complete combustion of a substance. Values of the enthalpy change of combustion may be obtained by direct measurement or from mean bond enthalpies. This data may be used to assess the efficiency of fuels. Petrol is a mixture of a large number of different hydrocarbons containing between 4 and 12 carbon atoms. Octane is a typical component of petrol. So in part A, the equation for the combustion of octane is shown. This is octane burnt in oxygen to produce that. They say Use mean bond enthalpies to calculate a value for the enthalpy change of combustion of octane. So here they've given us the bond enthalpies for the corresponding bonds that were used. So to calculate the delta H or the enthalpy change, we have to get the summation of bonds formed and the summation of the bonds that are broken. So the bonds that are formed are going to be 8 times 2 carbon oxygen, which is 16 carbon oxygen double bonds, and then 9 times 2, which is 18 oxygen hydrogen bonds. So if I have 16 times the carbon oxygen double bond plus 18 times that, we get that. This is the total from the bonds that are formed. And then the bonds that are broken, we have 18 carbon hydrogen bonds. You can count them here. Combining that, we get 16,088. So to find delta H, it should be summation of bonds broken minus the total bonds formed, which is this, minus that, giving us negative 5144 kilojoules per mole. And next they say the standard enthalpy change of combustion of octane is that. Give 2 reasons why this value measured under standard conditions is different from the value obtained using the bond enthalpy data. Bond enthalpy data are obtained as averages from different molecules or different compounds, and also they are obtained for compounds in gaseous state, but in this case we're talking about octane, which is going to be a liquid, so due to those differences these values are going to be different. So I said bond enthalpies are averaged values obtained using large number of compounds, and the bond enthalpies are for substances in gaseous phase, but octane is a liquid. The next, when petrol is used to power a car, the energy available is less than the theoretical maximum. When 1 kilogram of petrol powers a car, the energy used to move the car is 11 megajoules. Calculate the percentage of maximum energy that is available to move a car, assuming that this fuel is pure octane. The amount of energy is going to be Q, which is going to be negative delta H times N. Remember, we have the formula delta H is equal to negative Q over N. So I'm making Q the subject, which is negative delta H times N. So since we have the enthalpy change, I'm going to say the negative of the enthalpy change, converting it to joules. So I multiply this by 1,000, you can see there, to convert this to joules, times the number of moles. So this is going to give me that. But remember, they've told us 1 kilogram of petrol. So if it's 1 kilogram, that is the mass, which is 1,000 grams, divided by the MR of octane, which is 114, because they told us if petroleum is pure octane, they told us that if the fuel is pure octane, so it means I can use the molar mass of octane. I have that times that, giving me this. So the percentage maximum available is going to be 11 out of this total times 100, giving us 22.9%. And next they say give 2 reasons why the energy used to move the car is less than the theoretical maximum. Easy, this is incomplete combustion that could occur, as well as heat losses to the surroundings. And in part B, 2 alternatives to hydrocarbon fuels are hydrogen and ammonia. Hydrogen burns to form water as the only product, but hydrogen is extremely hard to liquefy. Ammonia is easily liquefied, but it is toxic. Compare and contrast the intermolecular forces involved when hydrogen and ammonia liquefy by describing how these forces are formed. We're comparing hydrogen and ammonia. So hydrogen can only form London forces, while ammonia can form London forces and hydrogen bonds as the major forces. Since we're comparing and contrasting, I have to talk about the similarities as well as the differences. So the similarities are both liquid hydrogen and liquid nitrogen have London forces between their molecules, and these London forces are formed between molecules because an even distribution of electrons in an atom of one molecule leads to instantaneous dipole formation, and these then induce a dipole in the nearby molecule. The attraction between the two dipoles is the London force. The strength of the London force depends on the molecular mass. Therefore, stronger London forces form between molecules with higher molecular mass, like ammonia, than those with lower molecular mass, like hydrogen. Now, the differences are, however, intermolecular hydrogen bonds are also formed between ammonia molecules, and this is because the nitrogen atom in the nitrogen-hydrogen bond is more electronegative. This creates a nitrogen-hydrogen bond which is polar. and the nitrogen atom also has a lone pair of electrons that can be used to form interactions with the partially positive hydrogens in the nitrogen-hydrogen bond of other ammonia molecules. So the overall intermolecular forces between ammonia are stronger and form more easily than those between hydrogen molecules, making ammonia to liquefy easily. So this brings us to the end of question 20. Let's continue to question 21. In question 21, methanol is used in the production of many materials and chemical compounds. It is manufactured from methanol by reacting with oxygen at 300 to 400 degrees Celsius using an iron molybdenum oxide catalyst. So they've given us this reaction here. The Maxwell-Boltzmann distribution for the reaction mixture at 300 degrees Celsius is shown. The first part says on the diagram sketch the Maxwell-Boltzmann distribution of this reaction mixture at a higher temperature. For the reaction mixture at a higher temperature, it goes in and then the peak is going to be lower than the one at a lower temperature. This is because the total area under the curve should be the same because they have the same number of particles overall. And then next I say, using the Maxwell-Boltzmann distribution, explain why increasing the temperature and adding a catalyst both increase the rate of reaction. When the temperature is increased, whether the reaction is catalyzed or not, the number of particles which have energy equal to or greater than activation energy are going to be more. We can compare those particles and the total in that whole area. We see there are more particles, or we can compare that in the first curve or the total, there are going to be more particles no matter the activation energy. In adding a catalyst, if we compare this one to be the uncatalyzed where this is catalyzed, because a catalyst creates a new pathway with lower activation energy, there are going to be more particles with energy equal to or greater than the activation energy when a catalyst is used. So I said increasing temperature increases the kinetic energy, so more particles have energy equal to or greater than the activation energy to potentially have successful collisions. Adding a catalyst creates a new pathway with lower activation energy, so more particles have energy equal to or greater than the activation energy for more successful collisions to potentially occur. And in part B, an alternative method for producing methanol uses silver catalyst at the temperature of 650 degrees Celsius. Their reaction is shown, which is this one here. They say suggest one advantage and one disadvantage of this method other than the cost of the silver catalyst. Here the advantage is hydrogen is produced as a byproduct and this could be useful in other processes, but the disadvantage is it has to be carried out at a higher temperature, which is 650 degrees, and this requires a lot of energy. Then in part C, they say explain how the infrared spectra of methanol and methanol can be used to distinguish between the two compounds. Methanol is an alcohol, so it's going to have a stretch for oxygen-hydrogen, while methanol is an aldehyde, so it's going to have a stretch for carbon-oxygen double bond. We can see here this is present in aldehydes like methanol, and this is present in alcohols. You can have the carbon-oxygen single or the oxygen-hydrogen for alcohols. So using the data booklet, we can find the wave numbers for the corresponding stretches. So I said we can distinguish using bond stretches present in one and missing in the other. Methanol has the following bond stretches missing in methanol. It has the carbon-oxygen stretch at 1740 to 1720 per centimeter, the carbon-hydrogen stretch at 2900 to 2820 per centimeter, and 2775 to 2700 per centimeter. Methanol has the oxygen-hydrogen bond stretch at 3750 to 3200 per centimeter, and this is going to be missing in methanol. In question 22, products used to clean toilets work in two ways, removing the lime scale that collects in the toilet bowl and disinfecting the bowl. Lime scale contains calcium carbonate, which is removed by reactions with acids. The strongest acid used in toilet cleaners is hydrochloric acid, although weaker acids such as methanoic acid are also used. Disinfectants are essentially chlorine dissolved in aqueous sodium hydroxide. The effective disinfectant in these solutions is the chlorate 1 ion, which is that. State 1 safety precaution that you should take when using a toilet cleaner containing hydrochloric acid. Hydrochloric acid is corrosive, so we need to use gloves as well as goggles. And in part B, the equation for the reaction of calcium carbonate with hydrochloric acid is shown. So here we see calcium carbonate, hydrochloric acid giving us that. They say write the ionic equation for this reaction. State symbols are not required. The ionic half equation is we do not split that, but we can split this. So since this and that can be split, the chlorides are going to be cancelled out. So we remain with calcium carbonate plus 2H plus, giving us calcium 2 plus water plus carbon dioxide, and that is going to be the answer. Next they say, a 750 centimeters cube bottle of a toilet cleaner contains 85 grams of hydrochloric acid. Calculate the maximum mass of calcium carbonate lime scale that could be removed by 50 centimeters cubed of this toilet cleaner. So I wrote the equation for the reaction. The mass for this is 85 grams. Remember, we have 85 grams in 750 centimeters cubed. And for HCl, MR is 36.5 gram per mole. So beginning with HCl, moles of HCl are going to be 85, which is the mass, divided by the MR, which is 36.5, giving me these moles. And again, this is contained in 750 centimeters cubed. So the concentration of this HCl solution is going to be number of moles over volume. The number of moles are here, the volume is here in decimeters cubed, and that is the concentration. So the moles of HCl in 50 centimeters cubed would be concentration times volume. This concentration times the 50 divided by 1000, again here converting the centimeters cubed to decimeters cubed. I got those moles. So moles of calcium carbonate removed by the 50 centimeters cubed of HCl will be 1/2 times the moles of HCl, since the ratio is 1:2, giving me that. The mass of calcium carbonate removed by 50 centimeters cubed of HCl would be number of moles times MR, which is this moles times the MR of calcium carbonate, giving me 7.77 grams as my answer. And in part C, chlorine gas reacts with water. This is the equation for the reaction. They say state the classification of this reaction. Justify your answer in terms of the relevant oxidation numbers. So we can see this is Cl in oxidation state 0, converted to oxidation state +1 and oxidation state -1. So this is a disproportionation reaction. So I said it's a disproportionation reaction. Chlorine is oxidized from 0 to +1 in this compound, and then chlorine is reduced from 0 to -1 in this compound. And next they say when 5 centimeters cubed of a disinfectant reacts with excess hydrogen peroxide, 113 centimeters cubed of oxygen is produced, measured at room temperature and pressure. So they've given us the equation. I wrote some components down here. This is excess. The volume of this is 5 centimeters cubed, and the volume of this is 113 centimeters cubed. So they want us to calculate the concentration in grams per decimeters cubed of sodium chlorate 1 in the disinfectant and give your answer to 2 significant figures. I began off by finding the number of moles of oxygen, which is going to be volume of gas divided by molar volume, using these conditions here, RTP. So 113 divided by 24000 gave me that. These are the moles of oxygen here. Next, I used the moles of oxygen to find the moles of sodium chlorate 1 using the mole ratio 1:1. So the number of moles are going to be the same. And therefore, the concentration of sodium chlorate 1 in 5 centimeters cubed is going to be number of moles over volume, which is the moles divided by 5 centimeters cubed. Here, I multiply times 10 power -3 to convert the volume to decimeters cubed. And these are the number of moles I got. So the next part was to find the concentration, which should be concentration in mole per decimeter cubed times the molar mass, which is gram per mole. So to find the molar mass of sodium chlorate 1, I added up all the components and got 74.5. So the concentration in mole per decimeter cubed, which is that, times the molar mass, which is 74.5, I got 70.15665, which is approximately 70 grams per decimeter cubed. Commercial disinfectants are often made more viscous by adding propane 1,2,3-triol to the aqueous solution. Suggest how propane 1,2,3-triol makes disinfectants more viscous. This contains 3 OH groups, meaning it can form a lot of intermolecular hydrogen bonds between the propane 1,2,3-triol molecules. So I said propane 1,2,3-triol contains 3 OH groups. This is per molecule that can form intermolecular hydrogen bonds. The hydrogen bonds strongly attract the molecules together, making the disinfectant more viscous. And in part D, toilet cleaners that remove limescale should not be mixed with chlorine-based disinfectants. Explain using the relevant equation why these two types of toilet cleaner should not be mixed. So here I included 2 reactions. The first one was a reaction of the disinfectant, which is chlorine reacting with water to give us that. And the other is a reaction in the cleaners to give us that. We can see that both reactions contain HCl, however this is reversible. If these two were mixed, the concentration of this is going to be higher, and this equilibrium is going to be shifted to the left, producing chlorine, and that chlorine is going to be toxic. So I said both reactions contain HCl. Combining them leads to higher concentration of HCl, so the equilibrium position in the reversible reaction shifts to the left, producing toxic chlorine. We will see there is a higher concentration of this based on the second equation I included. So in summary, you could have something like this taking place, meaning this reaction is going to be shifted. HClO plus HCl gives us Cl2 plus water. And in part E, borax is another cleaning agent used to remove limescale. Borax is a compound of sodium, boron, and oxygen. Borax crystals contain water of crystallization. The percentage composition by mass of some borax crystals is hydrogen 5.2%, boron 11.3%, oxygen 71.4%, and sodium 12.1%. Determine the empirical formula of the borax crystals and hence their formula. So here we have to show the element hydrogen, boron, oxygen, and sodium. The percentages are 5.2, 11.3, 71.4, and 12.1. And then to find the number of moles, we divide through by the atomic masses of the elements. So this by 1 gives us 5.2, 11.3 divided by 10.8 gives us 1.046, and 71.4 divided by 16, 4.463, 12.1 divided by 23 gives us 0.526. And next we divide through by the smallest number of moles in order to get a mole ratio. Here I get 9.89, 1.989, 8.485, and 1.00. I multiply through by 2 to create a whole number closer for this one here, which gave me a 2, 17, 4, and 20. So the numbers of waters had to equal to the hydrogens since all the hydrogens end up in the water. So it was very important for me to know water is going to be H2O. And since here we've got 20 hydrogens, so it's going to be 10, meaning the rest of the atoms are going to be in the remaining part. Just align them in the molecular form. So for example here, sodiums together, borons together, the remaining oxygens together times the waters. So this brings us to the end of section C as well as to the end of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.